Okay, part E. So there's lots of different parts of part E. There's six different parts, but they're all quite short. So she wants to create a model. She assumes income is independent, happiness is dependent. We already talked about that. She first considers a linear model of the form y equals ax plus b. Use Juliet's data to find the value of a and b. Okay, so guys, hopefully it's still there. It is. When I go into my calculator, I'll do it again just in case you're joining, you haven't watched the previous part, but I put in the data here. I've put in income and happiness, and I just go menu, statistics, stat calculations. Sorry, I'll do that again. Menu, statistics, stat calculations, linear regression. The X list is income. The Y list is happiness. Now note, I actually call them income and happiness, so it's clear what's going on. Save F2, that's fine. Results in there, okay. So I get A and B. Now guys, note, she's using A and B. My calculator is using M and B. So don't freak out. That's obviously A. So A is 0.000126. So A, okay, this is part I. A equals 0.000126, and B is equal to 41.149. 41.149. Okay, that's part I. Part II. Interpret, referring to income and happiness, what the value of A represents. The value of A. Okay, let me just do it up here, guys, because I have to write. So A is the gradient of this line, if you like, but what it actually represents in context is for every dollar increase, because X is dollars, so every time you increase a dollar, every time your income increases by $1, your happiness increases by 0.00126. So A is the increase in happiness score. And this question is asked a lot, guys. I've seen this question come up year after year. They want to know that you understand what's going on with what the line as a model represents. So it's the increase in happiness for every $1 increase. $1 increase in income. So when the X increases by 1, the Y increases by 0.00126. That's like, look, if you had an equation of a line, Y equals 2X plus 3. Every time you increase X by 1, you increase Y by 2. For example, if X was 5, Y would be 13, and if X was 6, Y would be 15. It increases by 2. That's the whole point. Okay, anyway, off topic. That's part 2. Part 3. She then considers a quadratic model of this form. Find the value of C, D, and E. So these are just different parameters, guys. She's not using A, B, C because she's already used A and B. So let's find C, D, E. This, guys, is also not that difficult to do. I have my numbers in here. I just need to go menu, statistics, stat calculations, and then I need to do quadratic regression here. Same thing. X is income, Y is happiness. That's fine. It's going to go into I. That's fine. Right. So here I have A, B, C. Now remember, guys, A, B, C is C, D, E. So just be careful. A is C. So A is C, right? So this is A, B, C, A, B, C. So just obviously be careful. C is minus 2.0619. C is equal to minus 2.0619. Now, guys, hang on. Okay, hang on. Be very careful. I thought that looked crazy. So and I was wrong, because look, this is minus 2.0619 e minus 9. So that means times 10 to the minus 9 times 10 to the power of minus 9. So that's a totally different number, obviously, than minus 2.0619. Right, so that's C. D is this guy's B. It's okay, this is written in this way, so look, let's just keep in scientific notation. So 7.05 times 10 to the minus 4. 7.05 times 10 to the minus 4. And E is equal to just 12.59. 12.59. Now guys, as I always say, just as long as you've more than 3 significant figures, you'll be okay. But if you want to round it to 3 significant figures, go for it. This one I haven't. This one I haven't. Anyway, fine. That's C, D, and E. Part 4. Find the coefficient of determination for each. The coefficient of determination for each of the 2 models she considered. Right, guys. The coefficient of determination is R squared. So for the, let's do the linear R squared equals, this will be in here, it's this one here, this is my linear, and my R squared is this guy, so 0.311056, 0.311056, and my quadratic R squared equals, quadratic R squared is not that one, just be careful guys, it is this one, 0.659146, 0.659146. Hence compare the 2 models. Okay, so part 5. So we're going to compare the 2 models, use, he says hence, so we're going to use this coefficient of determination. So the quadratic model, because the coefficient of determination is bigger, that means that it fits better onto the data. So the quadratic model fits the data better than the linear model, as I'm just going to write as R squared is bigger. Okay, finally, and this is a tricky question, guys. Juliet decides to use the coefficient of determination to choose between these 2 models. Comment on the validity of her decision. Right, this I've talked about this in my IA videos, guys. This is not valid. So I'm going to say not valid, because your R squared for the quadratic is always going to be bigger. Not valid, as R squared will always be bigger. Will always be bigger for the quadratic, for a quadratic. It doesn't mean it doesn't mean it's the best model. It doesn't mean it's the better model. And I'll just give you a very quick reason. Imagine you had these lines, right? 1, 2, 3. Now, well, actually, let me even give you some more. Imagine I had this, and even this. Now, if you do, this looks like a linear model, like this. And that's not a bad fit. But if you did like a, I don't know, if you did a, not a quadratic, but let's say a, hang on, you can find a model that will go through every single point, and the R squared will be 1. This is a quintic model. 1, 2, 3, 4. This is a x to the power of 5 polynomial model. The R squared would actually be 1. It's a perfect fit, but it doesn't actually mean it's the better model. So that's the kind of point they're getting to there. Okay, that, guys, is question 1, part E.